Hello everyone, I welcome you all to Startup Academy, India's only exclusive coaching for ISS examination. In the previous lecture, we were discussing about the mode of convergences, in which we discussed the mode of convergence in probability, almost sure convergence, in law convergence, and in arithmean convergence. And after that, we did weak law of large numbers. In today's lecture, we'll be dealing with another law of convergence, which is strong law of large numbers. In this, in the weak law of large numbers, we were saying that that x bar n converges to mu bar n in probability. When we were saying that we were discussing for weak numbers, weak itself suggested us that it was for it was not sure. But when we say we are talking about strong law of large numbers mean when n tends to infinity, then the strong law states that x bar n converges to mu bar n, that is any mean of the sequence x bar n converges to its own mean, which is mu bar n, will always converges to mu bar n in almost surely, not in probability. When we are sure of that, then we call it as strong law of large numbers. So today's topic is strong law of large numbers. It is also stated as SLLN. Okay. Now, when we talk about strong law of large numbers, let us suppose that xn, or let me take another pen. This isn't visible here. If we talk about xn, then xn be a sequence of random variables where n is always greater than equal to 1. And let us suppose that we are talking about Sn. Sn is nothing but summation of all the xi's, all the random variables. So we can state that uh, a sequence xn of random variables obeys strong law of large number if and only if expect Sn minus expectation of Sn upon n almost surely reaches to 0 as n reaches to infinity. This is the condition of our strong law of large numbers. I hope that you all can see here. This is our situation of strong law of large numbers. Okay. So strong law of large number itself says strong mean here means that we are talking almost surely. We are sure. Then only we will say that we are talking about strong. And large number is when n tends to infinity. This is the meaning of strong law of large numbers. Now from here we can denote that when something we can say when strong law of large number holds, then from this we can denote that weak law of large number also holds, right? When strong holds, weak will always hold. Means when almost sure holds that xn in almost surely converges to x, then we all can say that xn in probability will always converges to x, right? So when strong law of large number holds, then we can say that weak law of large number holds, or we can say that the convergence in probability also holds. That's it for strong law of large numbers. That is how we explain strong law of large numbers. So in a statement, we can say that when strong law of large number, SLLN, holds, then weak law of large numbers also holds. And when you have to give it an equation, you can say that when xn almost surely converges to x, then from this we can denote that xn in probability will also converge to x. This is our the crux of this statement. Now, moving forward, we have two more laws related to strong law of large numbers. Now, first is Kolmogorov's first theorem on strong law of large number. So, Kolmogorov's first theorem on strong law of large numbers. I'll be denoting it like this from here. So, I hope you'll be able to understand it. So whenever there is a random variable sequence, suppose xn is a sequence of random variable where n is always greater than equal to 1 and expectation of xi is mu I and variance of xi is given as sigma I square for all I goes from 1 to up till n. So if these situations have been provided to us that xn is a sequence of random variables and expectation of xi is mu I and variance of xi is sigma I square, then we say that strong law of large number holds only for the sequence when strong law of large number holds for sequence xn where n is greater than 1 if and only if summation I goes from 1 to infinity sigma I square upon I is less than infinity. Mean or summation I goes from 1 to infinity sigma I square upon I square exists. Okay. So, Kolmogorov's first theorem states that a sequence xn is said to be holding strong law of large number only when this has been provided to us that expectation of xi is mu I and variance of xi is sigma I square for all I goes from 1 to n, and this situation only holds when summation of I goes from 1 to infinity sigma I square upon I square is less than infinity or exists. Less than infinity itself means that it exists. Okay, and this law is also known as sufficient condition of strong law of large number. This is also known as the sufficient condition of strong law of large number. I hope that this theorem is clear with all of you. Now moving forward to Kolmogorov's second theorem. second theorem on strong law of large numbers. When we talk about Kolmogorov's second theorem on strong law of large numbers, then if xn here also is a sequence of random variable, is a IID, identically and independently distributed sequence of random variables, if this is the case, then we can say that and expectation of xi is equals to mu exists I'm sorry, and is finite for all I goes from 1 to up till n. So if this is the sequence that has been provided to us and of random IID random variables, and expectation of xi is mu, that means for every x's the expectation remains same, which is mu, exists and is finite, means it is less than infinity. Then we can say that xn almost surely converges to mu for all I goes to 1 to n. It is x bar n. Okay, so we can say that it or strong law of large number holds. Okay, so whenever we have been given the sequence of IID random variables and expectation of xi is equals to mu and expectation of xi is finite and it exists, then only we can say that strong law of large number holds, which in short can be written as x bar n almost surely converges to mu. Now here we haven't written mu bar n because all the expectations are mu. Let us say that if it converges to mu bar n, so mu bar n is nothing but summation I goes from 1 to n mu I 1 upon n. Now all the mu's are same for expectation of x1, it is mu, expectation of x2, it is mu, expectation of x15, it is mu, and expectation of xn is also mu. All of them are mu's, right? So here, instead of writing mu1, mu2, mu3, we can write it as 1 upon n into n mu. So n and n gets cancelled and we get mu bar n is equals to mu. So that is why we have kept mu here, not mu bar n. So this is the condition where we are solving for strong law of large number. This was all for strong law of large number. Hasn't been asked till now in the examination, but it is included in your syllabus, so that's why we have done it. There are no such questions to be done on this topic. This is a simpler topic. They might ask you what is strong law of large number or a definition if you would have known it, and there is no particular thing that they will ask in the exam only. They can change the pattern anytime. So this is also an important concept. I hope that I was being able to clear this concept for you all. And if you are still facing any doubts, then you can ask us in the comment section or on our WhatsApp channel. Only relevant doubts will be answered. And I would suggest you all to keep on revising, re-revising your syllabus again and again, and keep on asking doubts for whatever you are facing. And about our Lakshya batch 2027, enrollments have been opened for the admission of the batches. And if you are interested, you can enroll right now, or you can contact us on our WhatsApp channel for any details you want to know about our course. It will be starting soon after this exam of this year. 2026 is ISS examination, and we'll be starting with our new batch from the very beginning till the very end. So that's all for today's class. All the best. Thank you.
Startup Academy.